Hello, everyone. Thanks so much for joining me today. My name is Shannon Holmes. I'm a medical physicist with Standard Imaging, and it's my pleasure today to talk to you about the scintillation detectors. Before I get into the meat of the matter, I do want to stop and say from our family at Standard Imaging, we're hoping you're all finding a little bit of peace and a little bit of joy even amongst these uncertain and troubling times, sometimes troubling. Hope your families are doing well and that you are all healthy. So without a lot of, I guess I have a little more ado before we get going. A little housekeeping as well. I'm recording the webinar today. So if you have to step out in the middle or you want to share it with a colleague or just want to go back and review something later, you can look for a link to be sent out shortly, either this afternoon or tomorrow, of the recording. If you have questions at any time, feel free to enter them into the GoToMeeting dialog box. I'll try and answer those as I go along, but if I miss some, we'll certainly circle around to that at the end. And if you don't know a lot about us, Standard Imaging is based in Middleton, Wisconsin. We're just outside of Madison. It was founded just over 30 years ago in 1989 with a kind of modest suite of products as we got started, but it's grown quite a bit until to our current status now. We design and manufacture a full suite of QA products for radiation therapy. So why scintillators? Why did we go down this path? There are a lot of advantages of scintillators. They've been around for a while. These plastic organic scintillators that we're looking at are water equivalent for megavoltage photons and electrons. So you're not perturbing the beam right there at the point of measurement. This is particularly critical for those small field measurements that you're making, where the Bragg-Greg cavity theory doesn't really apply anymore because your detector starts to become, the size of the detector is comparable to the size of the field that you're measuring. And so those perturbations become pretty significant. The scintillators can be made very small, which is an advantage, of course, for those small fields as well. They have not shown dose or dose rate dependencies with these clinical beams or energy dependence. They have a beam quality correction factor of unity, which is extremely nice when you're looking at these energy changes with field sizes for small fields and the sort of corrections that you need to consider for all of your detectors down at those sizes. They've shown minimal energy dependence. We see about 0.1% per degree, which means that you don't have to correct for temperature if you're doing all of your measurements at room temperature. Someday, if we take this into patient measurements on skin or something like that, then you may have to correct for the temperature difference between your characterization measurements and your patient measurements. But we're not FDA cleared for that yet, so it's really not critical for just your QA measurements. The other nice thing is there are no metal parts in this optical fiber at all, and so we can use it with MR-Linacs. You do have to keep the electrometer, of course, outside the 5 Gauss line for that. So a little more detail about us. I mentioned we're using an organic scintillating material. Right now, the two options, the W1, which is our first generation device, is a 1 millimeter diameter, 3 millimeter long active scintillation region. With the W2, we have both 1x1 and 1x3 fibers. We were able to improve our collection efficiency to be able to go down to 1x1, which is really nice when you're looking at volume averaging, and that the orientation of the beam is not so critical. You do have to correct these scintillators for the Cherenkov light. This is a contaminant light that's produced within that optical transfer fiber. It's a PMMA optical transfer fiber. And that signal, because we're looking at an optical signal from the scintillator, we have this additional optical signal from the Cherenkov light that's produced within that optical transfer fiber. We have to have a removal method to get that out of the picture. So you're not affected by that, or your measurements don't change based on the amount of stem that's in the field. So we use a 2-channel chromatic correction that's based on a publication by Matthew Guyot et al. From 2011 in Med Physics. It's also linked on our website. And I'll explain that on the next slide here, just exactly what that entails. But it's shown to be, or it has been shown to be quite stable, and it's been working really well for us with the scintillators. So it's kind of a slick way to do that characterization and do that stem effect removal for the Cherenkov light. The scintillators are not absolute dosimeters. You can't send them in to be calibrated at the calibration lab. These plastics do change color as they accumulate dose, and that changes the way the color is transferred. You get decreased signal, and so they're not stable enough to be calibrated and sent back to you. So you would do a cross calibration if you want dose output as opposed to just like relative output factor measurements. You can do a dose calibration in-house, comparing just daisy chaining, basically comparing with a detector that you have calculated. Give the scintillator a known dose, and then you can convert the measurements into dose. Periodically recalibrate it as it accumulates dose. So that 2-channel chromatic correction is kind of shown schematically here. We have a blue scintillator, and the Cherenkov light is a broad range light. So we split this total signal up into what we call the blue channel and the green channel, the two portions of this spectrum. And we have you do a couple of characterization measurements. The idea here, this is the slab that comes with the W1. It's an option with the W2, but we have a smaller jig for that one as well. The idea is that you would make 2 characterization measurements. One we call minimum fiber, which is where you have the fiber coming straight out of this slab. And one is a maximum fiber, where you have a lot more of that optical transfer fiber in the field wrapped around like this in the outer channel. So the idea really is that you're keeping the dose to the scintillator, the active portion, the same. You're changing only that Cherenkov contribution. And so with that, we get a change in signal both in the blue channel and in the green channel. And so we calculate what's called a Cherenkov light ratio, which is that difference in the blue channel divided by the difference in the green channel. And with that knowledge, we can then correct subsequent measurements by removing a certain portion of signal based on the signal in the green channel from the blue channel in order to get rid of that Cherenkov contribution. If you're doing a dose calibration, you'd give it, there's a 10 by 10 field marked on here, or give it from a smaller field if you're using, say, CyberKnife. Give it a reference field size, a known dose at a known depth, and then you can also add in the conversion factor here for the dose. So the W1, the Exradin W1 was our initial device. It's been available on the market since 2014. It has that 1 millimeter diameter, 3 millimeter long active area. It's got a lot of publications available just because it's been out for that long, and it was quite a novel detector at the time. Well, still is, but the W2 has surpassed it slightly. The kind of exciting publication to me is a more recent one that was the joint publication from the AAPM and the IAEA. That was Technical Report Series 483 on small field dosimetry. And it has a lot of tables on the various detectors and correction factors for different beams as you go down to smaller field sizes. And every table that the W1 shows up in, it's got a value of unity across the board. It is the only detector in that publication that has that value. All other detectors, as you get to smaller fields, they start to need some correction factors. And some of them, when correction factors aren't listed, that means that the uncertainty was too high, and the committee didn't recommend use of that detector for those field sizes. So this greatly simplifies some of the issues with those small field measurements, knowing that there aren't those additional correction factors that you need to be considering as you go down in field size. The W1 still is a single point measurement system. It was designed mainly for output factor type measurements or output measurements. It does require a 2-channel electrometer like our Supermax in order to perform that Cherenkov subtraction calculation. You can do it by hand with other electrometers, but the Supermax has routines built into it, both for the characterization and dose calibration measurements, and then it will store those factors and apply those factors to subsequent measurements. So you just get the output in terms of either dose or that relative response with the Cherenkov removed. With the W2, this was our second generation device. We did make a dedicated electrometer for that has both the optics detection and the signal processing electronics. It's called the MaxSD for scintillation detector. It has a user replaceable fiber, this one, so you can use either the 1x1 or the 1x3 with the MaxSD. It's just a standard optical plug at the back of the device. With this electrometer as well, we can convert that Cherenkov corrected signal back into an analog output and send that current through a triaxial cable from the MaxSD into the input channel on your water tank for scanning. And you can use this with your scanning water tank to be able to scan your small fields. You have to scan slowly because it's a low signal device. You have to stop and measure. We recommend at least a second at each 12 point. But it's well worth it for the small fields to get accurate results that don't need a lot of additional correction. Some of the profiles from published data, this is from a publication from Indra Das's group at NYU Langone. Paulina Galavis is the first author on that one. But this is one of their plots that show 1x1 field measured in water compared with film. And they got excellent agreement between the two. They also compared it just to make sure that nothing had changed from the W1. They looked at dose rate dependence and dose dependence and that sort of thing. And they did not show either dose rate or dose dependence. Another fun publication out of Richard Popple's group, Jesse Snyder's the primary author on that one, looked at patient-specific measurements for small target sizes. So this is an image of the W2 within the detector plug of our stereotactic dose verification phantom, or SDVP. And you can see it's hard to detect where the end of the scintillator is. So we do actually provide a localization dummy fiber with a BB for the 1x1 fiber, or it matches the active point of measurement for the 1x1 fiber. So that group looked at targets all the way down to 3 millimeter diameter targets. It was the smallest one they looked at, and saw very good agreement between their film measurements and the W2 measurements. And I believe this was with Varian's HyperArc system. So if you have further questions, that's about all I was going to cover today. But if you have further questions, please feel free to visit our website or contact your sales rep at sales@standardimaging.com. I appreciate your time. I'm happy to answer questions if anybody has any. But otherwise, thank you very much, and have a wonderful day. There's a question from Yasmin. Is there anything these detectors can't do? They're not so good at big fields. They really are specifically targeted for small fields. Once you get into larger fields, then your Cherenkov correction provides a little more uncertainty just because of the magnitude of the Cherenkov signal compared to the magnitude of the scintillator signal. So they really are specifically for the smaller field measurements. Another question is, can we use the detector for Iridium 192 brachytherapy source? There has been a little bit of investigation into some HDR measurements, but again, the Cherenkov is a little bit trickier. There's a threshold above which Cherenkov is produced. And so I think there's another fluorescence dependency potentially with the HDR sources. So I know there are places that are investigating that, but that may not be the best use of our or the easiest scintillator to use for that particular application. We'd love to work with you on some research, though. If you want to contact me offline, we can certainly talk about that. How often is it necessary to recalibrate? Generally, the signal degradation that we see is you get about 2% decrease in signal for every 1,000 gray that you deliver to the fiber. And so you would want to recalibrate probably about every kilogray for the dose characterization. And then for the Cherenkov, sometimes it's, I don't think that decreases quite as quickly, but I would check it maybe about that same frequency and make updates if needed. I don't remember what people are doing right now. I do apologize. Is it easy to connect the W2 to a motorized tank? Yes, it's very easy to connect it. There's a triax cable that goes from the back of the Max SD to the input of your water tank. And from the point of view of the water tank, it looks just like a diode to your motorized water tank. You don't apply bias to it, but when the radiation is turned on, the water tank electrometer receives a current from it. So the Max SD does need to be about 1 meter away from the field if possible. The length of the W2 fibers is 4 meters long, so there should be enough slack for that to happen. And then the input goes directly to that input channel on your water tank. I think the biggest difficulty some people have had is the tanks that cannot provide an independent bias for the reference detector and the scanning detector to be able to scan with that without putting bias on the Max SD. It is protected, but we haven't done any studies to determine whether there's a change in the signal that your electrometer is getting if it's also putting that capacitance bias on the triax cable. We do provide an adapter sleeve with the W2 fibers so that it can be held by a standard chamber holder with your tank. I guess one of the other issues some people have had is that some tanks are very user-friendly when it comes to setting up their own brand of detectors, but they don't make it easy for you when you don't have a detector that is their own brand. And so the alignment can be a little bit trickier, and finding the center of the field and that sort of thing is a little bit trickier. Thank you. These are great questions. It doesn't look like I'm getting much more for questions, so thanks again, everyone, for your time. Feel free to follow up with us afterwards via email if that's if you think of something after the webinar ends. We'd love to chat with you some more.